because I had so many views on my first video talking about capacitance and capacitors. This is a second video. Anyway, I want to talk especially about electrolytic capacitors like they are here. When you are a little bit acquainted with electronics, you know that all, that's of course not new, electrolytic capacitors have a polarity. There's a positive here. In all these electrolytics, there's a positive here and a negative here, so you cannot reverse them in a certain electronic circuit. Positive must be connected to the positive lead and the negative to the negative lead in your electronic circuit. Well, electrolytic capacitors are, say, everywhere, also in the past, and even in the 1940s and 1950s. And when we are talking about these very old wet electrolytic capacitors, you could hear when you move them that the sound of the slosh of the water, say in a certain way water, of course not water, but it was an electrolytic, so it was immersed with ions. You could hear it, and I had, say, quite a few of them in the past, and well, that was interesting. Nowadays, many electrolytic capacitors, and then I mean, say, the standard ones that I've showed, don't have, say, a watery electrolyte. That water is more or less, in many cases, changed to a kind of moisture. In all these capacitors, there's a kind of moisture, and that is, say, the way that the electrolyte gives the two aluminum plates, in many cases aluminum plates, a certain capacitance. There are also many other electrolytic types of capacitors made with not aluminum plates. But anyway, I want to focus a little bit here on that, say, standard aluminum plate electrolytic capacitor with its moisture inside. And when you look at the World Wide Web and many electronics say sites on YouTube, there's always the idea, well, we have to replace the electrolytic capacitors because they are dried out. Is that true? Well, I really don't know. I mean that you have to test it with an electrolytic capacitor tester. And about electrolytics, there's a lot to tell. Anyway, their ESR, the time during which the moisture, in a certain way moisture, is moved out during temperature changes, etc., etc., into the air where the capacitor loses the electrolytic capacitor, that's what I mean, loses its properties, etc., etc. Well, that was the first thing to tell. Talking about electrolytics, here is again the same formula, and here we see the capacitance value, a calculation regarding the plates, the plates distance, and the electrolyte in between. I want to refer to my earlier video about that. Of course, when you have water as an electrolyte or a fluid electrolyte, that can differ very, very much in the capacitance, in the way that the capacitor acts, and well, that also refers in a certain way, because this is there's no fluid inside these capacitors, but anyway, moisture has also, say, a certain effect. And well, talking about electronic capacitors again, I use this old book, Handbook of Radio Technology of the 1950s, and here we see how the electrolytic capacitor works. The text is in Dutch, but anyway, perhaps I can try to give a kind of explanation. Aluminium oxide electrolyte. Here is, say, the way that such a capacitor is judged and can be calculated in electronic circuits. There's always a kind of resistance here. Has to do with the electrolyte, the properties of aluminium oxide, and the watery electrolyte. But well, this is kind of good idea about how to judge that, but in a chemical way, this is very, very complicated. So this book shows quite good ideas for practical electronics, but in terms of chemicals, there is, say, a kind of reaction when a certain voltage is added to this part of the capacitor and this part of the capacitor, and here we have aluminium oxide, and in a certain way that aluminium oxide eats itself a little bit into the anode in this case. Anyway, I don't want to get too deep in this issue, because well, I have to say that I'm not very, very good in, say, the chemistry about this setup. Anyway, when you want to do more studies, go to the World Wide Web, study the properties of electrolytic capacitors, etc. I stump a little bit through in this book. Anyway, they are talking about all kinds of capacitors. Let's say ceramic capacitors here. Ceramic, here's a ceramic tube, one silver layer, another silver layer, etc., etc. They are the opposite plates where the capacitance is realized. And here perhaps some other things. I will sum through a little bit to give more information. These are the so-called paper capacitors of the 1950s, and I surely have seen them and have had them in my store. And these are paper capacitors with a ceramic layer at their outside. So there's a lot to tell about capacitors here out of this old book. How a capacitor was made with metallized paper. They damped up a silver layer, or well, a zinc layer on that paper, and then you could build up a high value capacitor. And here we have, say, standard, well, this is a quite good example, 2.5 microfarad at 220 volts. Well, of course, nowadays in 2023 we don't see such a big capacitor. Modern plastics, modern insulation materials have changed this completely. Anyway, it's a good, say, site to study and, say, to see what was there in those days, 1950s, early 1960s. Well, it's a deviation of what I wanted to tell. Here there are electrolytic capacitors for a maximum voltage of 50 volts. They are electrolytic, but as far as I could see, they have polarity, but there are also non-polar capacitors for, say, the higher capacitance values. Anyway, what I wanted to tell, it's all about capacitors and capacitance. The capacitor, I've showed the formula, and well, I've also talked about fluid that can be used as an electrolyte. Often that electrolyte is, say, made with, say, certain ions used in that fluid. Well, perhaps I will give in the textbooks more information about, say, the specific fluids that were used to make an electrolytic capacitor. I have to think about it for a moment. And here we have, say, the standard AC resistance of a non-polar capacitor. My camera will stop suddenly within 45 seconds. This is the formula to calculate that value, and here the things that I wanted to tell, and I think I have told them all. Thanks for watching. Thanks for watching. Let's finish with this beautiful picture of a few capacitors.